Hello, my Algebra 2 students. Today you get to just listen to me. Sorry I can't be there with you, but we need to continue on, and I've got this lesson that we're going to go through today. So I'd like you to please have your books out, and I'd like you on page 117. And again, today, while the sub is showing this, he can pause the video anytime we need to. But today, the new topic that we're going to be talking about is called end behavior. It's about what the graphs are going to look like when we're taking a look at these different kind of functions. And it's really going to be focusing on that. Oh, I don't know why my pen doesn't want to write here, but we're looking at our leading term. That's the main thing that we're going to be noticing. So for our warm-up today for this notice and wonder, since I'm not there for you to notice and wonder, I guess I have to notice and wonder all by myself. Looking at these two graphs, I want you to pay attention to the fact that the exponents, the powers, or the degree of both of these are larger degrees. We've got a third degree on this first one. This is a third degree here, and a fourth degree over here. Because of that, they kind of flatten out on the x-axis. It's hard to see what the actual zeros would be. So I do notice that I can't tell exactly what the zero is in either of these functions. It's also something that I can see is that one of my graphs starts low down here and ends high. And this one, because it's got a fourth degree term, starts high and ends up here also with high numbers. Also, the y-axis scale is really large, right? Both of them are going from negative 8,000 up to positive 8,000. So I mean, we could wonder why they had to zoom out so much for this. I think that they probably were doing that to make it a little bit harder for us to see exactly what the x-intercepts would be on this. We could wonder, maybe, do all third degree polynomials look like this when they're graphed? Do all fourth degree polynomials look like this when they're graphed? Why do third degree polynomials look like this one that we've got here versus the fourth degree polynomial? The fourth degree, again, is the one where we've got, let me switch colors here, both ends are going in the same direction. And the third degree polynomial is where we've got different directions. We could wonder, does that always happen with third degree versus fourth degree? Does that happen because it's an odd exponent versus an even exponent? So that's something that we're going to be taking a look at. This table is in your book, and to save some time, I have this entire thing filled out. I'm not going to ask you to write down all of this. I'm going to ask you to look at some patterns for me, because some of these numbers are going to be really large. And this is something, if I was there in class, I would have you actually crunch these numbers. But if I'm not there, kind of a difficult thing to ask you to do without me. So I have this table all filled out. They're giving you different x values to substitute into these four different functions. One of them is a second degree polynomial, and then a third degree, and a fourth degree, and a fifth degree. They added one to each of them. So what I have in that x squared plus 1, if I guess we don't need to see those directions so much. The x values that we're putting into each of these functions are the same for all of them. We're going negative 1,000 up to positive 1,000 by factors of 10 in each of these. So the beginning and ending numbers are the same in this. And the fact that it's a square, an even exponent, that has something to do with it. But we're starting with really big numbers here and ending with really big numbers, and they match, right? And you can see that symmetry. these numbers are going to match, and these numbers are going to match, and these numbers match, right? And if you would think about what that graph looks like, and I'll show you in just a moment what that graph actually looks like. But the output part of that, it's going to start up really high and end really high on that. When we look at the next one, when it's a cubic, it's x cubed, that looks different. And we were just looking at a problem that had an x to the third power. I want you to look at these first ones. When the x is a really small number, the y is also a really small number, right? Take a look at that number right there, really, really small. And the numbers get bigger and bigger and bigger. And then when the x is 1,000, we've got a really big y value. So when the x is small, the y is small. When the x gets big, the y gets big. When I switch to a fourth degree polynomial, I want you to notice again that same symmetry that we noticed with the second degree polynomial. This matches this, right? We've got that symmetry when it doesn't seem to matter if the x's are really small, the y's can be really big, right? But again, this is going to match this. The y's start and end with really big numbers. And I'd like you to take a moment here. What do you think is going to happen when I've got a fifth degree polynomial? Do you think it's going to look like the second and fourth degree, or do you think it's going to look like the third degree? Hoping you can see a pattern here, but I couldn't even make the numbers fit so that you'd actually be able to see it. But a fifth degree polynomial with a really small x value, the y is really, really, really small. And it gets bigger and bigger and bigger until when we've got a really large x value, I've got a really large y value, right? So it starts as a really small y, gets to a really large y. Now, you can't really see this at the bottom of the screen. It says to sketch these. So I went to Desmos and I graphed each of them. This is the second degree. Again, it starts with the y's really high and they get low and then they come back up high again. If I look at the third degree, whoop, I can't do that. Sorry. If I look at this third degree one, and it still wants to, sorry, my computer's just not as fast as I want it to be. Let's try this again. If I can finally get my, here we go, come on. It doesn't want to move for me, and it's making me mad. There we go. Okay. This is the third degree one. It starts low and then goes high, right? It makes this kind of a squiggle shape. It starts low, kind of crosses over. They added one purposely so it wouldn't go right through the origin, and then goes up high. The fourth degree looks very similar to the second degree. It kind of flattens out a little bit in the middle here, but it starts high, comes down, and then goes up high again. And then the fifth degree. Very similar to the third degree. Starts low, slides over, again, kind of flattens out in the middle, and then goes up high again. But again, this lesson is all about end behavior. It's about the ends of the graphs. This one started low. This end is low. This end is up high. We have a certain way that we talk about that, and I'll tell you that in just a second. But the end behavior for this one is that it started high and it ends high, right? The y's are really large values here and really large values up here. Okay, so this is now on page 119. Let me see if I can make my pen actually do what I want it to do. page 119. We've got this really large polynomial, 2x to the fifth minus 5x to the fourth minus 30x to the third plus 5x squared plus 88x plus 60, all of those terms. It says identify the degree of the polynomial. The degree is all about the biggest exponent. So the degree is 5. Right? That's just what the biggest degree is, or but the biggest exponent is. For number 2, it says which of those 6 terms is the greatest when we substitute in these different values. So I want to put in 0 for x, or 1 for x, or 3 or 5. When I put in a 0, well, that's kind of nice because it would make this equal to 0, make this equal to 0, make this equal to 0, because if the x is 0, the whole term is equal to 0. So actually the 60 would be the greatest in that case. When I put in a 1, substituting 1 in for each of these, again, 1 to any power is just going to be equal to 1. So this first term would just be equal to, well, 2 times 1 is just 2. This one's going to be 5, and then this one's going to be 30, and 5, and 88, and 60. So 88x is actually going to be the largest term there. When I put in the 3, this one might take a little bit more crunching, a little bit more calculator work, and you can certainly try all of these. When we get bigger numbers, those bigger exponents are going to start to matter more. However, and we could certainly try this, but when you substitute in that 3, we're going to get 3 to the 5th power is 243 times 2. This first term would be 486. When I put 3 into the next one, 3 to the 4th power, that's 81, times 5, that's 405. 3 to the 3rd power is only 27, but 27 times 30, that number is 810. None of these other ones are going to get anywhere close to that. So 30x cubed is going to be the biggest one there. And for that last one, when x is a 5, when I substitute x to the 5th power, 5 to the 5th power, trying this first term, 5 to the 5th power is 3,125 times 2, that's going to be 6,250. When I do 5x to the 4th, 5 to the 4th power is 625 times 5. That's only 3,125. I can check that next one. 5 to the 3rd power is 125 times 30. That's 3,750. The other ones aren't going to get anywhere close to that. So 2x to the 5th power is the biggest one. That big exponent of 5 working with a larger number like 5 versus 3 or 1, that's what's going to get us that bigger answer. And when it asks us to describe the end behavior of this polynomial without graphing it, without looking at Desmos, because this has an exponent of 5, that odd exponent, and we've looked at one of those now, the way that we want to describe this, first of all, because it's an odd exponent, that means that the ends are going to go in different directions, right? When the x is negative, the y is going to be small. When the x is positive, like we had right here, the y is going to get really big, right? So they're going to go in different directions. The way that the book wants you to say this is, instead of saying as the x gets smaller or as the x gets negative, they want to say it this way. And to me, this is kind of weird. As the x gets larger in the negative direction, just means as the x gets smaller. the y gets larger in the negative direction also. So as the x gets smaller, the y gets smaller. As the x gets larger, the y also gets larger, right? So if we were looking at this as a graph, because it's got an odd exponent, I don't even care if you have any idea of what this graph is actually going to look like. It's going to start low and it's going to end high, right? That's the general idea of what that graph would look like. Okay, so today is all about end behavior, right? We didn't have a graph that actually looked like this, but we would be talking about what it looks like as the x goes farther negative or as the x goes farther positive. Whoops, I just switched those slides. So today, well, come on. My computer doesn't want to work with me. Here we go. Your homework today is on page 121 to 123. You've got problems 1 through 7. Monday, there's going to be a formative, but I will be back on Monday so I can answer any questions that you have. But just realize that I can answer any questions that you have if you want to email me. And if you just need to ask a quick question about any of this homework, feel free to reach out if you have any questions. I will see you guys on Monday.